All right. Wait, check this out. You know I would find the one song where dudes are rapping about 6 protons, 6 neutrons, and 6 electrons. That's carbon. Okay, let's keep it going. Let's talk about this. Energy and mass defect. So this is some weird stuff that we're getting into. And you know when we got a picture of Einstein and we see E equals mc squared, we're getting into some heavy, heavy stuff. So let's talk about this. And I like to kind of frame this as let's play Sim Universe. Remember that game, The Sims? Sim City and all that other stuff where you build up a city and you build up a town? Well, let's play Sim Universe. And so to do that, we want to start building up atoms. And we want to build up atoms from their fundamental components. So for example, if I wanted to create a helium nucleus, or in other words, an alpha particle, and really we're not even talking about making atoms yet. Let's just talk about making nuclei, bigger nuclei so that we can make bigger atoms. So to do that, right, we recognize there's 2 neutrons, okay, there they are, and 2 protons. And if I add 2 neutrons and 2 protons, I should make a helium nucleus, right? And so there's a question that I've asked here, is mass conserved? So in other words, if I take the masses from this table and add them up, do I get the mass of an alpha particle? And so logically, we would think, well, duh, of course, right? But this is where weird stuff happens. Okay, so let's do that. So if I had 2 neutrons, so that's going to be 2 times, and I'm going to use like all the sig figs from this table, 1.67493 times 10 to the minus 27, and that's kilograms, okay, plus the mass of 2 protons, 1.67262 times 10 to the minus 27 kilograms. And let's add that up. So I've got my calculator right here, okay? So we'll say 1.67493. And since all of this is times 10 to the minus 27, I'm just going to add that in later, okay? So I'll say times 2, okay, equals, and then now I'm going to say plus 1.67, let's see, yeah, 262 times 2 equals, that looks about right, okay? So that's going to be 6.6951, and then we'll even go because we had 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We'll add an extra 0 right there because we know that's significant. Times 10 to the minus 27 kilograms. So that should be the mass of our alpha particle. But look what the table says. Holy smokes. It is different, and this is not a sig fig thing. That is a significant difference, okay? And so if I take the difference between those, between these 2 masses, right? So let's say now minus 6.64465 times 10 to the minus 27 kilograms. This difference right here, which we'll say now minus 6.64465 equals, let's make sure that I did that right. Yep. So that difference equals 0.05045. So 1, 2, 3, 4, 5 decimals, 1, 2, 3, 4, 5 decimals. And that's 0.05045 times 10 to the minus 27 kilograms. And certainly we could say, that's the same thing as 5.045 times 10 to the, 1, 2. So that's going to be to the minus 29. This number right here is what we call the mass defect, okay? So if we take 2 neutrons, 2 protons, slam them together, we get a mass that's heavier than what's expected. And that is because some of that mass, the delta M, is converted into energy upon creating the nucleus, okay? And so we can relate that to E equals mc squared, which is really cool. And if you think about this formula for a minute, just the dimensional analysis, right? This delta M is a kilogram, and c, that's the speed of light in meters per second. So that becomes a meter per second all squared. And as it turns out, a kilogram meter squared per second squared equals a joule. So that's really all Einstein did with this equation, right? Is just dimensional analysis, right? To get the units to work. All the same, very powerful insights, okay? And so what happens with this now, we can actually use this mass defect to calculate the binding energy. So how much energy will get released when I create these nuclei, or how much energy I need to put in to separate these particles, right? So now imagine if I've got a helium nucleus and I want to rip my neutrons and protons back apart, I'm going to need this delta E binding energy to do that. So let's calculate that. So calculate the mass defect and binding energy for helium nuclide using the following reaction and masses of fundamental particles. So we already did that. We calculated delta M, okay? And so that was equal to 5.045 times 10 to the minus 29 kilograms. So that's our delta M. And so now to get our binding energy, we're just going to take that number and multiply it by the speed of light squared, okay? So that's going to go 0.045 times 10 minus 29 kilograms. Speed of light, you don't have to have that memorized. That's something I would give to you. But all the same, I have it written down here. 2.998 times 10 to the 8 meters per second, all squared. And so let's do that math. So over here, I'm going to say times 1e to the 27, negative, just so I can get that number in the calculator, right? There it is. And now I'm going to say times 2.998 e to the 8 equals, and then I should have said squared, so I'll just multiply it times another speed of light. Okay, and this doesn't look like a whole lot when I get this number. So it looks quite small, right? It's 4.53. We use 1, 2, 3, 4 sig figs. So 4.534 times 10 to the minus 12 joules. And that's technically joules per single nuclide, or joule per single helium nucleus. However, what if we made a mole of these things, right? Seems like a reasonable amount. We're gonna have a hard time making like one single nucleus, right? So what happens if we make a mole of them? Okay, well that would be times 6.022 times 10 to the 23, and I'll say nuclides per mole. And I'm also going to crank this up to the kilojoule unit just so we can compare it to numbers that we're used to, so 1,000 joules and 1 kilojoule. So now over here, if I say times 6.022 e to the 23, and then I'm going to divide it by 1,000. And let's see, now I get an enormous number. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 2.730 times 10 to the 9 kilojoules per mole. I cannot impress upon you how enormous this number is to create a mole of material. Or if I were to, split up this nuclei, that I would get that amount of energy. And I'll just compare this. So let's suppose suppose we have 1 mole of H2, okay? And I wrote HH because if now I go and combust this H2, if I release all of that bond energy, which you saw me do in the lecture, right? We blew up some hydrogen in the lecture. That's only going to give you 436 kilojoules for a mole of hydrogen. That's 1,000,000 times less than what we would get from the nucleus, okay? So we principally get energy from chemical bonds, right? When you combust gasoline in your engine, or when we look at a coal-fired power plant, we're getting energy out of the chemical bonds. However, you notice that if we could get energy out of the nucleus, which we do, and we'll talk about fusion and fission near the end of this material, you can see we get an enormous amount of energy out of the nucleus. And I want to impress upon you that if we can do that safely and responsibly, then in my opinion, this is the path forward for humanity. Being able to harness the energy that is in a nucleus and doing it in a safe and responsible way, that is going to be our path forward to unlimited, clean, free energy. Okay, so I'll see you in the next video.